This question was asked in the GATE Physics paper 2020. This is a MCQ having 2 marks. The topic of the question is quantum mechanics. The question is, the operator Sx cap denotes the spin operator defined as Sx cap equals to h cut by 2 times the matrix 0, 1, 1, 0. Which one of the following is correct? There are 4 options given. Option A, the eigenstates of spin operator Sx cap are up spin equals to 1, 0 matrix and down spin equals to 0, 1 matrix. Option B, the eigenstates of the spin operator Sx cap are up spin equals to 1 by root 2 matrix 1 minus 1, and this will be down spin. Down spin is equals to 1 by root 2 times the matrix 1, 1. Option C, in the spin state 1 by 2 times the matrix 1 root 3. Upon the measurement of Sx cap, the probability for obtaining up spin is 1 by 4. And the last option, option D, in the spin state 1 by 2 times the matrix 1 root 3. Upon the measurement of Sx cap, the probability for obtaining the up spin is 2 plus root 3 divided by 4. So among the 4 options, we have to choose the correct one. Let us see how to solve this problem. So it is given in the question that the spin operator, that is the x component of spin, Sx cap equals to h cut by 2 times this matrix 0, 1, 1, 0. Now this matrix 0, 1, 1, 0 can be written as sigma x, which is one of the Pauli matrix. So Sx cap equals to h cut by 2 times this Pauli matrix sigma x. Now we have to find what are the eigenvalues and eigenvectors for the spin operator Sx cap. So essentially we will find the eigenvalues for sigma x. Then we can easily find the eigenvalues for Sx cap operator. So essentially we will find the eigenvalues for sigma x, then we will multiply h cut by 2 with the eigenvalues of the sigma x or the Pauli matrix. So for that, what we have to do, we have to calculate this determinant, that is sigma x minus lambda times I2. So here lambda is the eigenvalue of the Pauli matrix sigma x and I2 is the 2 cross 2 unit matrix, and this determinant should be equal to 0. So if we write this whole thing in the matrix form, then it will become determinant of this matrix 0, 1, 1, 0, that is the sigma x matrix, minus lambda times the I2 matrix, that is 1, 0, 0, 1, that is equals to 0. So it will basically give determinant of minus lambda 1, 1 minus lambda equals to 0. So we will get lambda square minus 1 equals to 0. So lambda equals to plus minus 1. Hence the eigenvalues for the Pauli matrix sigma x are plus minus 1. So we will denote lambda plus equals to plus 1 and lambda minus equals to minus 1. These are the two eigenvalues for sigma x. So the eigenvalues for this operator Sx cap will be basically h cut by 2 times lambda plus and h cut by 2 times lambda minus. So the eigenvalues of this spin operator Sx cap are plus minus h cut by 2. Now we will find the eigenstates for this spin operator Sx cap. Let us consider uv represents the eigenstate of Sx cap. So it is also known as spinor. To find the eigenstates, what we will do, we will consider this Sx operator times the eigenstate uv equals to the eigenvalue, that is plus minus h cut by 2 times the spinor or the eigenstate uv. Now Sx cap is basically h cut by 2 times the Pauli matrix sigma x. So from both sides we can cut the h cut by 2, and sigma x is 0, 1, 1, 0. Then we can multiply this 0, 1, 1, 0 matrix with the column matrix uv, and that is equals to plus minus uv matrix. So it will give vu matrix equals to plus minus UV matrix. So we will get V equals to plus minus U. For the eigenvalue plus h cut by 2, we will have V equals to U. For the eigenvalue minus h cut by 2, we will have V equals to minus U. Let us choose U equals to 1. Then V equals to 1 for the eigenvalue plus h cut by 2 and V equals to minus 1 from this equation for eigenvalue minus h cut by 2. So eigenvectors or eigenstates for the spin operator Sx cap will be 1 1 and 1 minus 1, but they are not normalized. So in the normalized form, the eigenvectors or the eigenstates for the spin operator Sx cap will be up spin, that is 1 by root 2 times the column matrix 1 1, and the down spin, that is the 1 by root 2 times 1 minus 1 matrix. Now, if any spin state, that is the state or kate of phi, is given, upon the measurement of the spin operator Sx cap, the probability for obtaining the upspin state or downspin state of the x component is mod square of the inner product between upspin and phi state, or mod square of inner product between downspin and phi state. Now, let us check the options given one by one. So, option A, that is given the eigenstates of the spin operator Sx cap are upspin, that is 1 0, and downspin, that is 0 1. So this is false because we have already calculated the eigenstates or eigenvectors for the Sx cap operator is 1 by root 2 times the column matrix 1 1, and for downspin that is 1 by root 2 times the column matrix 1 minus 1. So this option is false. Now option B is given the eigenstates of this spin operator Sx cap are for upspin, that is 1 by root 2 times the column matrix 1 minus 1, and for the downspin 1 by root 2 times the column matrix 1 1. So this is also false because for upspin it will be 1 by root 2 times the matrix 1 1, and for downspin it will be 1 by root 2 times the column matrix 1 minus 1. So option B is false in this case. Now option C, it is given that in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap, the probability for obtaining upspin is 1/4. So in our case, the given state phi is 1 by 2 times the matrix 1 root 3, and upspin state, that is 1 by root 2 times the column matrix 1 1, that we have calculated in the previous slide. Now in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap operator, the probability for obtaining upspin state is given by P equals to mod square of inner product between the upspin state and the phi state, that is 1 by 2 times matrix 1 root 3. So this bra of upspin will give this row matrix, that is 1 by root 2 times the row matrix 1 1, and the state of phi state, that will be 1 by 2 times the column matrix 1 by 1 root 3, and we have to take mod square of this. So we can take out this 1 by 2 and 1 by root 2 from this mod square. So it will give 1 by 2 root 2 whole square times mod of the multiplication between these two matrix 1 1 and 1 root 3 and mod of this square. So this will give 1 plus root 3 mod square whole square, and this will give 1 by 8. So we'll get effectively 1 plus 3 plus 2 root 3. So this is the 1 plus root 3 whole square divided by 8. So it will give 4 plus 2 root 3 divided by 8, and after simplification it will give 2 plus root 3 divided by 4. So it is not matching with our option C. So option C is false in our case. Now option D is saying in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap, the probability for obtaining upspin state is 2 plus root 3 by 4. So this is true because we have already calculated this probability in the option C. And from the option C, we have found that the probability will be 2 plus root 3 divided by 4. So the option D is correct in our case. So according to our solution, the last option, option D, that is in the spin state 1 by 2 times matrix 1 root 3 upon the measurement of Sx cap operator, the probability for obtaining the up spin is 2 plus root 3 divided by 4. So this is the correct one for this question.